eventually want to make substitution of cosine, which means we want to separate the derivative of cosine, which is over sine after minus, and express all the rest as a function of cosine. So sine squared is over cosine squared left. We can express sine squared as a function of cosine. It's just 1 minus cosine squared minus cosine squared. Now remains substitution of cosine and du is minus sine x dx. Once we have this, we have the integral 1 minus cosine squared, which is u squared, divided by cosine squared, which is u squared. Sine of x dx is minus d times minus d. So it's minus the integral of 1 minus u squared divided by u squared du. This integral, well, it's the integral of a polynomial divided by power of the variable. So we can do some simple algebra. Right hand form 1 over u, 1 over u squared minus 1 d. Now we can integrate this integral of 1 over u squared. So 1 over u squared is equal to negative 2. So we apply the formula u to the power n plus 1 over n plus 1. So it's minus u to negative 1 divided by negative 1 and minus integral of 1 is 2 plus constant. Simplify it a little bit. So it's 1 over u plus 2 plus constant. Finally, remember that u is in fact cosine x. So let's see. And please don't make the mistake of writing the final answer of the integral of all function of x in terms of u. It just doesn't make sense. The integral of function of x must be a function of x. Okay, so any questions about this? Once again, the way you try to make this function cosine was just, well, remember, when I see sine to the whole power multiplied by a function of cosine, cosine is a derivative. And vice versa, if I have cosine to the whole power times some function of sine, substitution of sine makes sense. Alright, so last time we seen last time we have seen a couple of classical functions in which we know how they these were trigonometric integrals, sine to some power, cosine to some power, secant to some power, tangent to some power, integrals with expressions like square root of number minus x squared, or square root of x squared plus a number, or x squared root of x squared minus 1. So we've seen integrals of such expressions. And today I want to devote the first hour to talking about integrals of rational functions. Turns out that first of all, they appear quite frequently, and the second thing, they're quite easy to compute. So we start with integrals of rational functions. And these are integrals of such expressions. One polynomial divided by another polynomial. already know how to find some of these integrals. So, for example, integral of 1 over x plus 2 with this integral. So if it were just 1 over x, the integral would be just lowering the absolute value of x. This one is 1 over x plus 2. Well, we can either guess that it's lowering the absolute value of x plus 2 and check that it works by differentiating this function lowering the absolute value of x plus 2. Or we can make a substitution using x plus 2 du dx. So this is integral of 1 over du, which is 1 absolute value of 3 plus constant, which is 1 absolute value of x plus 2 plus 1. So this integral of 1 over x plus 2, well, just lowering the absolute value of x plus 2. Very simple integral. Questions about this one? Let's try another example. Slightly harder. Integral of x plus 3 divided by x plus 2. What about this one? So, any ideas how to find this integral? Yeah? So the idea is to do some, well, algebraic magic. To write it as x plus 2 plus 1 divided by x plus 2. What does it give you? Well, it gives you the option to rewrite this. It's just integral of 1 plus 1 divided by x plus 2. And now it becomes very simple as this. Integral of 1 is x. Integral of 1 over x plus 2 is 1. It's the value of x plus 2. Alright. So we do know some simple integrals like this. It is a little bit harder to find such an integral if in the numerator and denominator the function is not linear, not just x plus number, let's say quadratic or cubic, starts with x cubed, x squared, and so on and so on. But we'll get this. In fact, most of the functions, most rational functions, or it's a slight exaggeration, I would say all rational functions, can be brought by some algebraic manipulation basically to such a problem. Sum of integrals of 1 over x plus 1. And what we want to do is to learn this algebraic thing. It's called partial fractions. So what are those? The idea is, so here's the fact. If degree of the numerator, the degrees at the highest power of x which appears in the numerator. So here it was 0 because it's 1 times x to the power 0. Here it was 1. So if the degree of the numerator is smaller than the degree of the denominator, then factor. So if you have a polynomial, you can try to factor it as a product of linear factors. X minus x1, x minus x2, x minus x10. So like the quadratic polynomial, which you can find the two roots, x1, x2, and write it as x minus x1, x minus x2. But with any polynomial, we can write any polynomial can be written in this form. Product of x minus its roots. It's well, a little bit not true when we talk about real numbers, so we'll just restrict ourselves to such polynomials which can be factored, but in fact, well, if you learn math a little bit deeper, you'll know that any polynomial can be written in this way. So suppose that the polynomial is already factored. Then, and also say different size. So I don't want any repeated factors. Then P of x over Q of x, this fraction, complicated fraction, can be written inside the way. A number divided by x minus x1 plus a number divided by x minus x2 plus and so on plus a number divided by x minus x10. Yeah?
With different x, what? X?
X5. So x1 is not the same as x2, it's not the same as x3, it's not the same as x4. So all these numbers, x1, x2, x3, x4, is different as x1, x2, x3. So it turns out that any polynomial, any rational function is just a small condition. The degree of numerator is smaller than the degree of denominator. Can in fact be written this way. And this representation of the rational function is called partial fraction representation. So let's look at an example. Let's say we start with a function which is over x squared minus 1. It is a rational function, that's one thing. The degree of numerator is 1, the highest power is x to the power 1. The degree of denominator is 2, x to the power 2 is the highest power. So we have this condition, the degree of numerator is smaller than the degree of denominator. The denominator can be factored quite easily as a product of linear factors. So x squared minus 1 is in fact x minus 1, x plus 1. And this fact tells you this function can be written in different forms using partial fractions. Like this. Some number divided by x minus 1 plus some number divided by x plus 1. So this statement just tells you there are some numbers A1 and A2 for which this identity is actually true. Our task now is find these numbers A1 and A2. So how to do it? Well, let's just make this equal to that. So let's make this fraction have exactly the same form as this. So it will bring this thing to the common denominator. So now I see how to go about finding this A1 and A2. What I want to do is, well, the denominators are already there the same. The numerators, well, they might be different, but the same depending on the one they do. So if we try to make them equal to each other. So we'll make the x plus 5 equal to statement where it's using that you will be able to find such numbers A1, A2, which will satisfy this identity. Now, how to find it? There is a simple trick. These things are polynomials. They should be equal to each other for any value of x. Choose a convenient one. For instance, if I want to find A1, let me get rid of A2. How will I do it? How will I do it? Plug in x equal to 1. This will take care of this term. It will become 0. Then this becomes 7 is equal to A1 times 2. So A1 must be 7 over 2. Let's do a similar trick. Find A2. I want to try to get rid of this term. I'll plug in x equal to minus 1. This bracket will become 0, and what will be left is 2x minus 1 plus 5. 3 is A2 times negative 2. So A2 is minus 2 plus. So now I know both A1 and A2. Now I have this identity. X plus 5 divided by x squared minus 1 is 7 halves x1 over x minus 1 minus 3 halves 1 over x plus 1. And this identity is just true. You can bring these things to the common denominator, do the algebra, you'll get exactly this expression. So before we go into a summary of what happened here and how to repeat it in other examples, why did we even bother? The reason is this expression is much simpler than this for what purposes. If you want to integrate. If you want to integrate this expression, you basically have no idea. Integral of some rational function, I don't really have in mind a whole bunch of functions because derivatives are rational functions. But in this form, it's quite obvious how to integrate. So if I want to find the integral of x plus 5 over x squared minus 1, I would instead integrate this thing. I can go from here to here, it's just a matter of algebra. This thing is exactly the same thing. But in this form, it's quite obvious what it is. It's 7 halves times 1 times 7 over x minus 1 minus 3 halves 1 times 7 over x. So what this representation allows you to do is integrate. So the situation is somewhat similar to maybe opening the brackets. If you want to integrate x plus 1 times x minus 1, it's not obvious how to do it. But once you open the brackets, you instead integrate the same thing, x squared minus 1. Now suddenly you know how to do it. So the same thing. You have a rational function, but now the algebraic manipulation is called partial fraction decomposition. So you decompose this function in the sum of these single fractions, and you integrate each one of those. Now, what is actually the process? Well, so the process is like this. We have a fraction and rational function. First thing, you check the degree of numerator small than degree of denominator. It's important, we'll see what happens if it isn't, but for now, check that it is. Once it is, try to factor the denominator as a product of linear factors, which means x plus some number, x minus some number, x plus some number, something like this. Once you have the factors, write this expression with unknown a1, a2, a3, and so on. As many a's as there are factors. You still don't know what those a's are. To find those, bring this new fraction to common denominator. And try to equate the numerator of this expression to the numerator of the original. That's what we did here. From here, try to solve for a1, a2, a3, and so on. And a convenient trick is try to plug in some numbers and make most of the terms there 0. So we'll see an example in a second. First, questions about this one. Okay, so let's look at a little bit more complicated example. Something we read. So let's try to find the integral of x over x minus 1, x minus 2, x minus 4, dx. So here the denominator is already factored for you. Check that the degree of numerator, which is 1, the highest power of x is 1, is smaller than degree of denominator. What's the highest power of x denominator? So it's 1 each of the factors, but there are 3 factors. So we go to the brackets, you will see powers of x as high as x cubed. The degree of denominator is 3. 1 is smaller than 3, so this statement tells you you can compose it as a sum of partial fractions. So this expression, for which you don't see a obvious integral, can be rewritten in a simpler form. A1 over x minus 1, a2 over x minus 2, a3 over x minus 4. So this statement tells you it can be done. Your task is now to find the corresponding the a's which go a1, a2, a3. So let's take this expression and bring everything to the common denominator. So we have to multiply this fraction by x minus 2, x minus 4, which gives me a 1, x minus 2, x minus 4. Multiply this fraction by x minus 1, x minus 4. Multiply this fraction by x minus 1, x minus 2. Alright, so we brought everything to the common denominator. We see that the denominator on the right side and the left side is exactly the same. The numerators must be made equal. So we want x to be a 1 times x minus 2, x minus 4, plus a 2, x minus 1, x minus 4, plus a 3, x minus 1, x minus 4. let's find A1. Find A1, I'll try to plug in a value of x which will make this thing and this thing 0. What value of x will they choose? X equal to 1. Yes. So 1 x equal to 1, then this becomes 0, this becomes 0, so we're all going to get 1 is equal to 1 times minus 1 times minus 3. So we're all going to get 1 is equal to 1. Let's find A2. To find A2, I'll plug a value of x, which will make this 0 and that 0. There is exactly one value like this. So plug in x equal to 2. What you get is 2 is equal to A2 times 1 times A2. So A2 is negative 1. Finally, for A3, I will plug in something that means this 0 and this 0, which is x equal to 4. 4 is equal to 0, 0, is 3 times 3 is 2, so 3 is 2 thirds. Well, now we have coefficients. We can compute the integral of x over x minus 1, x minus 2, x minus 4. dx should be the same as follows. Not only the integral, the expression itself, if you have done the calculations correctly, should be the same as 1 over x minus 1 x third minus 1 over x minus 2 plus 2 thirds 1 over x minus 4. And the integral is 1 third 1 over x minus 1 minus 1 x minus 2 plus 2 thirds 1 0 over x minus 4 plus 1. So, in a way, this operation of taking a rational function and decomposing it as a sum of simple fractions, sum of partial fractions, is the opposite process of bringing to the common denominator. Instead of taking simple expressions, bringing them to the common denominator and getting a complicated one like this, you start with a complicated one and you write it as a sum of simple ones. But with different denominators. Questions about this integration? The next question is, what happens if the degree of the numerator is not smaller than the degree of the denominator? What if we are increasing something like, well, we have an example, x plus 2 divided by x plus 1. The idea was to rewrite this as a sum. 1 plus a fraction like 1 over x plus 1. So, in fact, we can do it always. If degree of numerator is at least as large to divide one by the other, one polynomial by the other, with remainder, and you transform this expression where the degree of numerator is larger than the degree of denominator. To an expression like this, a polynomial, which is of course very simple to integrate, plus another rational function, but now the numerator is smaller than the degree of denominator. So let's do an example of this procedure. Let's say I want to integrate so I want to integrate 3x plus 2x2 plus x squared plus x plus 2 and all this divided by x squared plus x plus 2. Degrees of numerator is none. The highest power of x in numerator is 4, highest power of denominator is 2. So unfortunately, degree of numerator is not smaller than degree of denominator. 4 is larger than 2. So I cannot just decompose it as a sum of partial fractions. What this tells me is I can try differently. I can try to take this polynomial and actually divide by that polynomial with remainder. Write it as something times x squared plus x minus 2 plus some remainder. Now how to? Well, the procedure is called long division. If you know long division of numbers, it's exactly the same procedure, not just polynomials. So the procedure works like this. I want to divide 3x to the fourth plus 2x cubed plus x squared plus x plus 2. I want to divide it by x squared plus x minus 2. What is the code? What you do is you try basically to guess the answer term by term. The first term is to take care of the highest power of x here. So the first question is, if I want to multiply x squared plus x minus 2 by some polynomial, and get 3x x to the fourth plus some small terms, smaller order terms, what kind of answer can I expect? Well, if I want to multiply x squared by 3x squared, I'll get 3x to the fourth. So let's try. Now, what happens if you actually multiply x squared plus x minus 2 by 3x squared? What you get is 3x to the fourth, which is a good thing. But then we have plus 3x squared, then 3x cubed, and minus 3 minus 6. So the highest powers do match, lower powers do not. There is a difference between this polynomial and the product of these two polynomials. What is the difference? Well, you can find it. I'll just take the difference. This minus that. So no terms like this. There are terms here. So minus x cubed plus 7x squared plus x plus 2. So I just subtracting this polynomial from that. Now I can try to go even further. I have this polynomial, which is the difference. I can try, well, to make the difference smaller. I can try to divide this polynomial by that polynomial. Once again, the first task is just to kill one of these polynomials. So multiply x squared plus x minus 2 by minus x, I will get some polynomial which starts with minus x squared, which is good. Unfortunately, not good enough. So if I multiply x squared plus x minus 2 by minus x, what I get is minus x cubed minus x squared and plus 2x. So these polynomials are not quite the same. Their difference is the polynomial a x squared minus x plus 2. I continue in the same way. This difference can be further divided by this polynomial. So if I want to take care of this term 8x squared, I will just multiply this polynomial by 8. If I do multiply this polynomial by 8, I don't quite get this. I get x squared plus 8x minus 16. And the difference between what I want and what I get is minus 9x plus 18. And that's it. I cannot go any further. I cannot take this polynomial and divide it by quadratic polynomial, because this is degree 1. So if I multiply the rest of the polynomial by any polynomial, I'll get something to degree at least 2. I can't get something to degree 1. So overall, I have found this fact. My polynomial is denominator, in numerator, is in fact x squared plus x minus 2 times that polynomial, x squared minus y plus 8. But not quite. We have to add this remainder. So this whole process just shows you if you take this polynomial and subtract a multiple of x squared plus x minus 2, which is this multiple of the power, you'll get this remainder. What does it tell about the fraction? This polynomial divided by x squared plus x minus 2. Well, it tells you that 3x on the 4 plus x 3 plus x squared plus 2 divided by x squared plus x minus 2 is just 3x squared minus x plus 8 and plus this one. So after this long division, we get this result. Our fraction can be rewritten in a simpler way. This polynomial plus this fraction, which looks a little bit less scary. In fact, it is exactly what we know how to deal with. We know that it can be rewritten as a sum of partial fractions, a sum of numbers divided by x minus number. So before we take care of this term, any questions about this long division? Let's make a poll. How many of you have previously seen long division of polynomials? Okay. How many of you have seen long division of numbers? Okay, so if you haven't seen this long division process, a good idea would be, well, either open a high school algebra book or Google long division of polynomials and try to do some exercises. It's basically quite a mechanical process. It can be done pretty fast once you get used to it, and well, it is useful for us when we are expected to know it in the end. Okay, we are left with one model which we still don't know how to integrate easily. This is this thing, minus 9x plus 18 divided by x squared plus x minus 2. We don't know what we talk about for our kids. A function whose derivative is exactly this one. But we can rewrite this as a sum of partial fractions. For this we know degree of numerator is smaller than degree of denominator. That's what we worked so far to achieve. The denominator can be factored. Can be written as x minus something, as x minus something. So these numbers can be found either by solving the quadratic equation, x squared plus x minus 2 is equal to 0, using the quadratic formula, or in this particular case, they're easy to guess. So the product should be minus 2, the sum should be 1. So what are these numbers? So it's minus 1 plus 2, yes. So it's minus 1 plus 2. Minus x plus 2x is x, minus 1 x 2 is minus 2. Once you have factored the denominator, you can write a partial fraction equation. The only thing that remains is find this a1 a2. So bring it back to the one denominator. a1 plus a2 plus a2 plus 1. I want these to be equal to that. So 1 in x equal to minus 2 and x equal to 1. The first one gives me a2 minus 3 is equal to 46. So we do this minus 12. And this one gives me 1 minus 3 is equal to 2. So a1 is 3. And finally, I can compute the integral. The integral of 3x to the fourth plus 2x cubed plus x squared plus x9 plus 2 divided by x squared plus x minus 2 dx. Integral of this awful expression is in fact the same as the integral of much simpler expression. 3x squared minus x plus 8 plus 3 divided by x minus 1 plus minus 12 divided by x plus 2. And now this integral is quite obvious. It's x cubed minus x squared over 2 plus 8x plus 3 1 plus 12 minus 1 minus 12 1 plus 2 plus x. So once again, the process of finding integral of a rational function is as follows. If the degree of the denominator is smaller than the degree of the numerator, write the function as a sum of partial fractions minus the efficiency and so on. If it is larger, first, as a preliminary step, the whole long division. And then you are left with a similar task. remainder divided by the denominator can be written as sum of partial fractions, and then just one small comment. Sometimes it happens that the polynomial of the denominator either has multiple factors like x minus 1 squared or x minus 1 cubed. It doesn't happen frequently, but it happens. Or it is something which cannot be factored, at least in real numbers, something like x squared plus 1. It's not x minus something, it's x minus something, it's no rules. We won't deal with these situations in this course, but they are, in fact, not really part of this thing. So they're not more complicated, it's just related with what we want to do. But you should remember that in principle, every rational function can be integrated using some kind of automated sequence. So let's make the 9